5.2 The Maxwell-Boltzmann distribution. The particles in any gas or solutions are all moving at different speeds. A few are moving very slowly, a few very fast, but most are somewhere in the middle. The energy of a particle depends on its speed, so the particle also have a range of energies. If you plot a graph of energy against the fraction of particles that have that particular energy, you end up with the curve shown in figure 1. This particular shape is called Maxwell-Boltzmann distribution. It tells us about the distribution of energy amongst the particles. Now, a few points to remember. No particles have zero energy. Most particles have intermediate energies, around the peak of the curve. A few have very high energies, the right-hand side of the curve. In fact, there is no upper limit. And finally, note that the average energy is not the same as the most probable one. For a reaction to take place, a collision between particles must have enough energy to start breaking bonds. See topic 5.1. This amount of energy is called the activation energy EA. If you mark EA on the Maxwell-Boltzmann distribution graph, then the area under the graph to the right of the activation energy line represents the number of particles with enough energy to react. The need for the activation energy to be present before a reaction takes place explains why not all reactions that are exothermic occur spontaneously at room temperature. For example, fuels are mostly safe at room temperature, as in a petrol station, but a small spark may provide enough energy to start a combustion reaction. The heat given out by the initial reaction is enough to supply the activation energy for further reactions. Similarly, the chemicals in a match head are quite stable until the activation energy is provided by friction. Even the high temperature of a single spark can set off a reaction. This is why if you smell gas, you must not even turn on a light. The electrical connection provided by the switch could produce enough energy to begin an explosion. The shape of the Maxwell-Boltzmann distribution graph changes with temperature. At high temperatures, the peak of the curve is lower and moves to the right. The number of particles with very high energy increases. The total area under the curve is the same. This is very important. It's the same for each temperature because it represents the total number of particles. The shaded areas to the right of the EA line represent the number of molecules that have greater than EA at each temperature. The graphs show that at a higher temperature, more of the molecules have energy greater than EA, so a higher percentage of collisions will result in a reaction. This is why reaction rates increase with temperature. In fact, a small increase in temperature produces a large increase in the number of particles with energy greater than EA. Also, the total number of collisions in a given time increases a little as the particles move faster. However, this is not as important to the rate of a reaction as the increase in the number of effective collisions, those with energy greater than EA.